same way. Yeah, it's hump day. You're halfway through. All right, so I believe yesterday we were kind of reviewing function notation. But depending on where a value is placed, it's kind of telling us if we plug it in for an x or if we plug it in for a y. And we were starting to analyze yesterday, once we do some calculations, what do the numbers kind of represent in terms of a graph? Okay, so we're trying to make that connection or representation. Did we leave off on page 40 and did we find these x values? But that's as far as we got. We didn't answer any of the questions? No? Okay. So just as a refresher from yesterday, we set our f of x parabola equation equal to 0 in the first block. We set it equal to -4 in the second block. And solving through for x, we actually ended up getting 2 x solutions for each problem. So we're going to take a look at graphically, where are these numbers showing up on a picture, okay, of that same parabola graph. So when we solved the f of x equals 0 question, okay, that was our first block up here, what do the results represent graphically? Can we think about what these 2 x solutions mean or where they might be showing up on the graph of f of x? Yeah. They're x-intercepts. Good. Okay, so when you have a y value of 0, notice how we set the equation equal to 0, just like a normal equation is equal to y. The x solutions are x-intercepts. So graphically speaking, -1.586 looks like it's somewhere right there. And -4.414 looks like it's somewhere right there. Okay, so we'll say the x solutions represent the x-intercepts. Okay, but that's only for this first example. Okay, when the y value is 0, those are giving you the x-intercepts. Okay, on the other hand, what about if we checked out the other one we did? What if we had a y value of -4? Okay, where are the solutions of -1 and -5 showing up on the graph? Can we describe where they might be? Can you maybe give me an ordered pair where they might be on the graph? Yeah.
-1, -4, and -5.
All right, good. So the points, x value of -1, y value -4, and the other point, x value -5, y value -4, are on the graph. And let's try to plot those. So -1, -4 looks like that's on the graph. We can clearly see that. And -5, -4, we can clearly see that one as well. So in the first one we did, the y value of 0 was giving us the 2 points on the x-axis, whereas the second one we were doing was giving us the 2 points on the graph for a y value of -4. Okay, they're in different spots. Okay, so graphically speaking, we have a way of connecting the algebraic work that we did. Okay, we did that at the top of the page, solving by hand, but we can make sense of it in terms of a picture. Okay, there's a connection between what the numbers are telling you above and how they look on a graph. Okay, everything's connected. So kind of in summary, just so we know the different notations, if we were to plug in a number into the f function, what does that number represent? And if we were to set a function equal to a number, what does that number represent? I know it's the letter A, but we're just going to say A is some number, whatever you want it to be. So there's a difference in the way these two notations look. We need to be familiar with what they're actually telling us. So what's the difference between a number inside the function and the number equal to a function? What do you think, Tori?
One of them is x and one of them is y.
All right, so that's an x value and this is a y value. So whenever you have f of a, okay, a is representing an x value, which means the answer you would get, okay, the result if you were to plug in a would be a y value. Okay, on the flip side, if you set an equation equal to a, aka a y value, the result would represent an x value. You plug in an x, you get out a y, or vice versa. You plug in a y, you get out an x. Okay, and if we know an x and a y, we know an ordered pair, which means graphically we can plot that point, okay, in terms of a picture. Okay. Remember doing this kind of earlier this year, a little bit? Okay, we're going to step it up a bit today though, and instead of looking at a parabola, we're going to start to look at some of those parent functions we've been talking about, like absolute values and square roots, and maybe some some cubic graphs. So in terms of this particular function, we're going to go ahead and answer some different questions. So take a look at the first one. Notice how -6 is inside the function, so that's representing an x value. They want us to find the value of -6. Now we're going to do it two ways, okay, just so we're familiar with both. We're actually going to find the value by hand, okay, using some algebra because we have the equation. But then once we have our result, we're going to make sure it actually makes sense by checking it on the graph. Okay, so let's go ahead and we'll plug in -6 into the x in the equation. And let's go ahead and see what we get out. Be careful with absolute values. Anything negative becomes positive. Can we get -1? Okay, so algebraically, okay, by hand, the answer is -1. Let's make sure that that answer makes sense graphically. So what is this algebraic work telling us in terms of the graph? What should the point look like, or where should the point be located? Go ahead, Hannah. -6, -1. Okay, so let's go on the graph. -6, -1. Looks like we did our algebra correctly because that point is actually on the graph. Okay, everything's checking out. Let's go ahead and try the next one. This time we have an x value of 1. Algebraically, by hand, looks like we get -2. Let's make sure it's confirmed we did the math right by the graph. So this is telling us that the point 1, -2 should be on the graph. And looks like it is. Okay, so far so good. Let's switch it up a bit. Instead of plugging in a number for x, maybe we'll check out if we plug a number in for y. So this time we're going to set our absolute value equation equal to -4. How do you guys want to start solving for x? Yeah, Ashley? Let's add 5. Bless you. So that would give us 1. What about from there? This is when it can get a little tricky. It's probably been a while since we've done absolute value equations. Okay? Remember how when we did factoring, you would break up every factor and set it equal to 0? Okay? There's something similar to that. Okay? If you think about the definition or what it means to be an absolute value, anything inside that's positive stays positive, right? But anything inside that's negative changes to positive. So you kind of have two things you need to check. What if your inside was positive? Or what if your inside was negative? So what we're going to do is kind of break up this absolute value into those two different pieces. What if the inside, meaning x plus 2, was equal to positive 1, like this equation's telling us? Or what if the inside x plus 2 was equal to negative 1? Okay, we have two possibilities that might be inside this absolute value that would be giving us an answer of 1. Do we remember having to do that with absolute value functions? It might be a while, but maybe it's coming back. So we actually got to check this out twice. If we subtract 2,
Excuse the interruption. At this time, I need juniors, last names A through F, to report to the auditorium for pictures. That's juniors, last name A through F. Thank you.
anybody in here? No? All right, so notice how for this single y value, we actually have two x values. Okay, we saw that with the parabola on the last example. So graphically speaking, we should have the point -1, -4, but also -3, -4. We have two x's associated with the same y. So let's see if that makes sense graphically. -1, -4, looks like it's on the graph, but also -3, -4 is on the graph. Okay, so when it comes to absolute values, you're definitely probably going to have to break it up, because most likely we're going to have those two solutions because we have those two stems. Okay, one going in each direction. Let's go ahead and check out the next one. What if our y value is 5? Maybe you can follow the algebraic work that we did on the last one as an example. Bless you, very similar steps. Can we get 8 and -12? Okay, so graphically speaking, we should anticipate the points 8 and 5 on the graph, but also -12 and 5. It might be a little difficult for us to check this one based on the picture they gave us, because notice how the highest y value they provided was 2, but we wanted a y value of 5. So we can't really see it. But if we were to extend the legs, this one definitely looks like it would be going towards the x value of 8. And if we were to extend this one, it definitely looks like, bless you, it would go towards -12. Bless you. Okay? So might be hard to check depending on the graph that's given to you. If you wanted to take the time to actually extend it to check it, you could. Okay, but notice how if we did this correctly, we could probably trust that this one's correct as well, right? Okay, do you guys think you can try the square root one? Give it a shot. Okay, go ahead and check out the 4 examples algebraically, and then try to confirm them based off your graph. Make sure your algebra makes sense in terms of the picture. Someone with a calculator, can you help us out? -2 times the square root of 5. I think it's -4 something. 4/7? Okay. Thank you. Bless you. All right, how'd the first two work out for you? Plugging in a number for x, getting out a y? Typically that's the easier one for people to do, okay? Are your results checking out graphically? They making sense? Okay, probably hard to check the second one because the graph doesn't go all the way out to 10, but if you trust that you did this one correctly, again, you probably did that one correctly, okay? What about if we switch it up and set equations equal to numbers? These can be a little tricky because there's a lot of movement or solving involved. Do we want to go over any of those processes? Okay. How do you get rid of a square root? What'd you do? Yeah, square both sides. Okay, so as long as you can get the square root by itself, okay, notice how we got rid of the 3 and then the -2 out front. As long as you can get the square root by itself, you can square both sides. And then from there, you can do one more step to solve for x. Are your results checking out graphically? Okay, if they weren't, you know you did something wrong, right? So you may have to go back and check it. Okay, we doing okay? Perfect. Okay, so the last thing we're going to do today, we're going to take a look at a free response type question, okay? We're eventually going to start doing these in groups or with pairs in here. Not every day, okay, just kind of random throughout the year. But you're going to see questions like this kind of show up on our unit tests, okay? So a free response type question is basically giving you one piece of information at the top and then somehow asking you multiple questions about that one piece. Notice how we have parts A, B, C, and D. So what we're going to do this one together, okay, but eventually I'm going to give you some time to do some other ones on your own as we get more familiar with them, okay? So for this free response type question, consider the piecewise function, and we're going to use this one function to help us answer the rest of the questions throughout the problem. Okay, so for part A, they want us to find the values of p of -3 and p of 4 if they exist. Okay, hopefully we realize sometimes you plug in a number, but you might not get anything out. Okay, that means it doesn't exist. There's no point there. So they go on to say if a value doesn't exist, we need to explain why, okay, using words. You might feel sometimes this year that you're in an English class, okay, because we're going to do some explanations. I want a sentence or two about what you did or what your results mean, okay? Maybe that's something you're not used to in a math class, okay? So let's go ahead and tackle this one. What is the p of -3 and p of 4 telling us to do? What's that notation mean? Go ahead, Ashley. Plug it in for x. Okay, so if we were to plug in -3 for x, we have to be a little careful with that because we have a piecewise function. So we have to determine which piece, okay, which equation are you plugging in -3. You're not going to plug it into all of them, okay, we're just going to pick the one that it fits. So how do you think we can determine of the 3 which one we would plug it into? What do you think, Tori? The what? Why the middle one? Okay, so this one says equal to 3, but we're plugging in -3. It's okay. Okay, so I love how Tori's looking over here. Okay, this is your domain section, right? Those little pieces are telling you which x values you can plug in for the particular functions. What do you think, Marie? Why? Okay, so notice how the first one ends at -3 and the second one kind of begins at -3, right? So you kind of see that showing up. Maybe you think it's both. But what did you say about the bar piece?
They wouldn't be a filled circle.
It wouldn't be a filled circle, okay? You would have an open circle at this one and another open one at that one, right? Okay, so if you have an open circle at -3, does the actual point exist? No. Hannah, were you going to say something?
No.
Are you sure? Okay, so notice how even though both of these have that -3 x value, neither this one nor this one can actually equal it, right? There's no bar for either of them. So in this case, we would say that this point does not exist. You can use DNE for short if you want to. There's no closed circle at that location. Okay, so we have to explain this. Okay, if a value does not exist, explain why. This point doesn't exist because, what are some explanations, or how might you want to phrase it? Everyone might say something different, but as long as your justification is including the correct mathematical terms and
Excuse me,
such.
interruption. At this time, I need Junior's last name G through M to come to the auditorium for your pictures. G through M. A reminder that all students need to get their picture taken, whether you're purchasing pictures today or not. So if you did not go the first set, please go. And this group, G through M, all juniors.
All right, good, Hannah?
But none of the domains include -3.
Okay, because none of the domains include, you could say equal, okay, because we don't have that equal bar, okay, whatever terminology you want to use, because none of the domains include the x value of -3, something like that. Some of you may say the first equation has an open circle at -3, the second equation has an open circle at -3, meaning there's no closed circle, so the point doesn't exist. Okay, there's multiple ways or phrases you can go about for your justification. I'm just looking for some explanation. Okay, let's go ahead and check out the other part of this question. We got to find P of 4. So take a look at your domains again. Which piece, which one equation are you going to plug in for? Go to Rachel.
Is it the third one?
How do you know?
I thought the third one, because if you plug in the 4,
Mhm.
I kind of say it out loud in my head.
Yeah.
-8 is less than or equal to. It only makes sense in the third one.
It only makes sense here, right? Notice how the number 4 is between 3 and 8. Okay, so that x value is pertaining to this domain, so we're going to plug it into that particular equation. So let's go through and solve. This means we're actually going to have a closed point on the graph. Okay, the point exists because we are able to plug in that particular number. And it looks like we'll get -4. Okay. So piecewise functions can be tricky because sometimes you might not have a point, sometimes you will have a point. It all depends on that domain, whether you have those open circles or closed circles, those bars or no bars. Okay? We doing okay? If I were to give that to you on your own, do you think you would have been able to figure those two pieces out? Maybe? Okay. All right, so the second question is asking us to sketch an accurate graph of P of x. So remember, P of x is that piecewise function at the top. So just like we were doing the last few days, we're going to try to graph all 3 of those pieces. Do you guys want to do that together, or do you want to try that on your own? Now that we've had some experience with it. Do you feel confident, or do we need a little refresher? I see smiles, but I have no idea what they mean. You gotta give me some words, people. Go, Marie? No? Don't care? You wanna do it on your own? Thank you, Rachel. Okay, give it a shot. I mean, I'm going to do it on the board so you can follow as I go, okay? But see how far you can go on your own.
How we have -1 as an answer for both the second
Mm-hmm.
equation and the third equation,
Yes.
and one's a closed circle and one's an open.
Uh-huh.
Do we just like leave it closed? and
Okay,
open?
great question. So notice how for the second equation, it's -1, but that's exactly where the third one picks up, okay? This -1 should be closed because we have a bar. This one should be open, okay? So if you have the same point, but one's closed and one's open, the closed one is actually filling in that open one, okay? So it's going to remain a closed dot there, okay? If you're checking your work with what's on the board, the L and U stand for left and up in terms of that vertex point for the V. Okay, instead of starting at the origin, you can move it left and up. And then the same thing going on for the parabola. You can move the vertex right and down from that origin to help you figure out that guiding point. Okay, we're going to utilize those transformations. How'd you guys do? Pretty good? Awesome. Okay. So let's continue with this one. So now that we have a graph, yeah, sorry.
Okay, for the first one,
Yeah.
I think what point did what x value leave it?
For the first equation,
Yeah,
if you plug in -8,
no, for your vertex. Like I did the -8 and the -3.
you did that. Okay. So to figure out the vertex, you're going to utilize that left and right, up and down transformation.
Okay.
So it moved left 6 and up 7. So instead of the vertex starting at the origin, if you move it left 6, up 7, it's now there. Okay? Okay, the negative out front's just telling you it's flipped. Notice how that makes sense because we have a V going down. And the 2 is that vertical stretch. So instead of having a normal V, we stretched it, which kind of pulls the legs up. It makes it narrower. Okay, so notice how the V looks a little steeper than an actual V would. Okay, so that's what the 2 was doing. The left and right, though, moves the vertex to a new position. Anything else on the graph? All good questions. All right, so take a look at C. Now that we have a graph, we're going to explain in words how this graph validates our computations from part A. So if you take a look at part A, we said that the point at -3 doesn't exist, but we also said that the point at 4 does exist. Specifically, we get an answer of -4. So how does the graph you just drew validate those two algebraic computations? What are some phrases or words you might want to use for your explanation? Go ahead, Marie. Okay, so the points that existed, so that was P of 4. P of 4 equals -4 exist on the graph. How do you know they exist? Can you tell me like where it's located? Say it again. Sorry. From the third equation, okay. So from the equation it exists, that's what we did in part A. But where on the graph is this computation showing up? What do you think, Tori?
In that first area, it's on the line.
It's on the line. Okay, so right, the first barrier right here? Is that the one you're talking about?
No, sorry, I was looking at that.
That's okay. If this is what we got algebraically, okay, what does that represent in terms of a graph? AKA a point. What would the point look like? Go ahead, Marie. The shaded, this one? That shaded point? Can we write the ordered pair? Go ahead, Marie. There we go. Okay. So the point exists, or this information exists on the graph because that specific point is on the graph. Okay, so again, we're making the connection. We have the algebraic representation, P of 4 equals -4, and we are transitioning or connecting that to the graph. meaning the point is on the graph. If we check it out, 4, -4 is right there. Notice how that's on the parabola, that third equation that we used to find it? Okay, so graphically that's making sense. What about the other computation we did? P of -3, we said that doesn't exist. How is this graph confirming that finding? Go ahead, Rebecca.
The two places where there is -3, there are open circles.
Are open circles. Graphically speaking, okay, we don't have a closed circle there, right? So P of -3 doesn't exist because there is no closed circle on the graph at the x value of -3. So we're taking the algebraic work and using the graph to help us check it out, okay, confirm it, but we got to make sure we can analyze the graph appropriately. Okay, how can we figure out that the algebraic computation was actually correct? Okay, again, that one may have been a little tricky because there was no math involved, really. It was just all explanation, but we're trying to get familiar with what these different numbers and notations are telling us. Okay, the last one, we're going to practice some domain and range. Remember, domain are x values and range are y values. And I think when we did some examples of this previously, we went with the lowest x value to the highest x value. Do you remember doing that? How far left it goes, how far right it goes? Okay, so if you were to take a look at this graph you drew, what's the furthest to the left that your graph would start or go? Can we figure out that x value? Can you find it, go, Tori? -8. Can you touch -8? Do we have an open or a closed circle there? We've closed, right? Okay, so we can touch it. Do we remember what symbol we use to signify that we can touch that point? We can equal that point? Yeah. It's a bracket. Good. Okay. So this is kind of our beginning point, and as we travel across the graph, notice how we kind of have an issue when we get to -3 because there is no point there, right? We said there's an open circle. So even though we start at -8, we have to show how we stop at -3 because there is no point at that x value. And if there's no point, you can't touch that location. We use a parenthesis. But we have more graph, right? Okay, so what we're going to have to do is write another interval signifying a beginning point and an ending point. So if we continue to work through our graph, we're going to skip over that -3. Notice how the first interval ends with that value, but the second one begins with that. We're skipping over just that one point because we have open circles there. And as we continue to trace our graph, notice how we can touch every single point until we get to 8, right? And we can't touch 8, so we have another parenthesis. Okay, so think about where does your graph start, and as you trace it, can you touch every single point? We eventually got to a place we couldn't, so we had to end that interval. But since we have more graph, we have to make sure we include another interval for that piece. Now there is a symbol that we're going to put in between these two intervals. It looks like the letter U, stands for union. It's like we're merging or marrying these two together. Okay, these two intervals apply to this one graph. You've heard of a civil union before, like a marriage. Okay, that's what the U stands for. It stands for union. Okay, we're going to do the same thing for the range. So instead of tracing it left to right, we're now going to figure out what's the lowest point that the graph begins, and then if we were to continue up, what's the highest point that it ends. So can you take a look at your graph and figure out the lowest y value? Good, Marie? -5, can you touch it? Yep, closed circle. Okay. Now this is when you go, yeah, go ahead. All right, so here's the tricky part. So notice how you start at -5, right? And I want you to imagine if you were to trace or drag your pencil, okay, going up the graph, there is a hole at -3, correct? Okay, but don't you have closed circles over here as well? Okay, so even though you can't touch -3 here, you can touch -3 here. As long as you can touch a portion, you're going to keep dragging your pencil. Okay, we're just concerned with when do you never touch any portion of your graph. That's when we have to jump over that particular section. So it can get tricky. The range can be a little difficult. Even though this is an open circle, you're still touching a portion of your graph over here. So we're going to continue to trace our graph. Okay. Notice how we get to another issue at 1, but even though this is an open circle, we're still touching it over here. So we're still going to drag our pencil. We eventually get to 3. We have an open circle here, but we can still eventually touch our graph, right? So we're going to keep dragging our pencil. When does our pencil stop? Go ahead, Marie. 7. And you can touch 7. So again, the range is going to be tricky. We're eventually going to have more examples of this when we get into the actual domain and range section. But as long as you can touch a portion of your graph, you will continue to trace or drag your pencil until you can't. Yes, ma'am? We would continue, right? Because even though you can't touch one, you can't touch the other. So we would keep dragging, okay? Very, very good. Okay, so that was our first free response type question. Okay, we'll eventually see more throughout this unit and throughout the year. I might start letting you do some on your own or in a group, okay? But this is kind of the format you're going to see. You're going to be given some information at the top, and you're going to be asked multiple and different questions about that one particular piece. Okay, we're going to get used to that format. Are we doing okay? Perfect. All right. That's it for this section. So any of the homework that you may have not started or gotten to yet on page 43 or 44, you should be able to tackle tonight. Okay? Or at least try some out. Deal? All right. Have a good day, guys.